In this video here, we're going to take a look at testing the goodness of fit with discrete data. Now, this video here will largely focus on which distributions you need to be able to perform goodness of fit tests for, as well as how we estimate parameters if necessary. So, starting off with then, the distributions that we will perform goodness of fit tests for, and there's 4 distributions here that we're going to focus on. So the first one is a discrete uniform distribution. Now, we have actually already seen an example for this here. We saw that in the previous video on testing a hypothesis. So if you'd like to see an example for that, do go back and check the previous video on testing a hypothesis. We then have a binomial distribution, then a Poisson distribution, and then for the final distribution here, this is a little bit special. So this is the geometric distribution. And the reason that I say this is special here is because we cover this in a separate video. And the reason for that is because the first 3 distributions here are all considered part of the first year material, whereas the geometric distribution is for second year material only. Okay, so if you're only doing the first year material for Further Stats 1, don't worry about the geometric distribution. Okay, so for this video here, we won't be looking at any kind of exam style questions. What we're going to do here is just take a brief look at each distribution, as well as discussing how we estimate the respective parameters. Okay, so you won't always need to estimate the respective parameters. If you do need to, it is important that you know how to do that. And then finally here, we calculate the test statistic the same way for each distribution. So recall from our previous videos here, we used the following result. So x squared, our chi-squared value, this is our test statistic. And this is equal then to the summation here of the observed minus the expected. We square that difference and we divide it by the expected frequencies. Okay. Let's take a look then at testing a discrete uniform distribution as a model. Now, we have already seen an example here of testing a discrete uniform distribution as a model. We did see that in the previous video here for testing a hypothesis, and that was for the example then of rolling the 6-sided dice. Now, you need to be aware here of the conditions under which a discrete uniform distribution is likely to arise. And we have 2 conditions here. So for the first condition then, we say that each value is equally likely. For the second condition, we say that the discrete random variable x here is defined over a set of k distinct values. Now, for the expected frequencies here, so for a sample of size n, they're given by the following result here. So the frequency, the expected frequencies here are equal to n times 1 over k. And then finally here, for a discrete uniform distribution, we will never need to estimate a parameter. So that's good for us, right? Makes life a little bit easier. So for that reason then, our degrees of freedom here will always be 1 less than the number of cells. So that gives us everything that we need here then for testing a discrete uniform distribution as a model. Let's take a look then at the second distribution here. So this is for testing a binomial distribution as a model. So again, you need to be aware here of the conditions under which a binomial distribution is likely to arise. Now for the binomial distribution here, we have 4 conditions. So for the first condition here, we say that we have a fixed number of trials, which we denote as n here. For the second condition, we say that the trials are independent. For the third condition, we have 2 outcomes, which we denote as success and failure. So success is p, failure would be 1 minus p. And then finally here, for the very last condition then, we say that the probability of success here, p, is constant. Now, you should be very much familiar with all 4 of these conditions here. This is just the binomial distribution, right? So for the frequency then, f subscript r here, with which each r occurs when the number of observations is n, this is given by the following result here. So as you can see then, f subscript r is equal to the PMF then for a binomial distribution. So that's the probability that our random variable x here is equal to r, and we times it by our sample size then n. Okay. Now sometimes we may have to estimate our parameter p here. So to do that, we need to use the following result here. So p is equal to the total number of successes divided by the number of trials times by n here. And then mathematically, the way that we define that here is sigma bracket r times f subscript r divided by n times by n here. Okay, so that might look a little bit confusing on the surface here, but we will see that as we work through our examples here for testing the goodness of fit with discrete data. So don't worry too much about that for now. And then finally here, if we have to estimate P, so that's our parameter P here, the probability of success, using the above result, then our degrees of freedom here, so this is nu, the Greek letter nu here, this represents the degrees of freedom, that is equal to the number of cells minus 2 there, because we have 2 constraints, right? So if we don't have to estimate P, as we can see here at the bottom, using the above result, then our degrees of freedom here, nu, is equal to the number of cells minus 1. Okay, so again, do take a note of all of this here as we work through this. It is really important that you're aware of all of these properties here. So that gives us everything that we need here then for testing a binomial distribution as a model. And finally then, let's take a look here at the very last distribution here for this video, and this is for testing a Poisson distribution as a model. So again, you need to be aware here of the conditions under which a Poisson distribution is likely to arise. And again here, we have 4 conditions. So for the first condition then, we say that the events occur at a constant rate. For the second condition, we say that the mean and variance are equal. For the third condition here, we say that the events occur independently. And then finally here, for the very last condition, we say that the events occur singly and at random. Now, it's not actually related to this, but is it just me, or does the word singly never actually sound like a real word? Singly? Maybe it's just me. But anyway, I digress. So the frequency here, f subscript r, with which each r occurs, is given by the following result here. So as you can see then, f subscript r here, again, is equal to our PMF then, in this case, for a Poisson distribution. So the probability that our random variable x is equal to r, and then we times it by our sample size here again, n. Okay. Now, sometimes we may have to estimate our parameter lambda here. And to do that, we need to use the following result here. So as you can see then, lambda here is equal to sigma. So this is r times f subscript r. We divide it by n here, where n is our sample size. Okay. And then finally, in that case then, if we do have to estimate lambda here using this result, then our degrees of freedom, again, just as we saw for the binomial distribution here, is equal to the number of cells minus 2. However, if we don't have to estimate lambda here, our parameter lambda then, using the above result here, then in that case, our degrees of freedom here, nu, is equal to the number of cells minus 1. Okay. So hopefully all nice and straightforward here just to get us started. So in terms of the geometric distribution, as I mentioned at the very beginning of this video here, we will cover that in a separate video. Okay. So if you want to see how goodness of fit works for the geometric distribution, do go check out that video. Okay. So that actually brings us to the end then of this video here on testing the goodness of fit with discrete data. In terms of the practice questions here, what I'll do is I'll do separate videos for each one of these examples here. So a discrete uniform distribution, binomial distribution, Poisson distribution, and as I said then, the geometric distribution will be covered in a separate video. Okay, so there we have it then. As we said, this brings us to the end then of this video here on testing the goodness of fit with discrete data.